As we said last video, we had a bit of a crisis on our hands. We didn't know how the atom could be stable. You had a positive nucleus and negative electrons that somehow stayed in stable orbits around the nucleus without crashing into them, right? Positive nucleus, negative electrons, how come they don't crash? Well, maybe they have a sideways velocity, but then that would mean they're accelerating, which would produce waves and release energy. This doesn't happen, so we don't know how they could be stable. In comes de Broglie, okay, or it looks like de Broglie, but in comes de Broglie saying, well, I know this smart guy, right? His name's Einstein. He said that photons could be both waves and particles, or in fact, they're neither. Photons could have the properties of both waves and particles. So why can't particles also have properties like waves, such as the electrons? So his idea was that the electron going around the nucleus was actually going around in a wave. So waves have uh, waves have a length, and that length wraps around the whole nucleus. So it's not really accelerating. It's not going back and forth. It's existing around the nucleus, kind of solving a problem. Also, we had these quantized energy states. That is that an electron can have certain amounts of energy around an atom, but nothing in between, right? So de Broglie said that the electron waves around the nucleus had to be a standing wave. That is a wave where you can fit a whole number of wavelengths in the circle. So just to give you an idea of what I mean, so the first standing wave was when you could fit one whole wavelength, boom, around the nucleus. So if we have the nucleus here, and if we were to fit this around the nucleus, that would just look like a circle like that, yeah? If we're fitting two whole wavelengths, boom, around the nucleus, then down, up, then I think that would look something like this. We've got a stretched out thing where you can see these two spots here are the two crests, and these two spots here, boom, boom, are the two troughs. Yeah, you with me? I think from here it starts to look a bit more intuitive. Our third one, wait a sec, let me just draw some points so that I don't stuff it up too much. Our third one has to come up, in, up, in, up, in. Oh, that was not drawn very well. And you can see that if the wavelength, like I've just done there, is not a standing wave, it's something in between, there's going to be a mismatch. So I obviously did not draw that very well. Let's go up, in, up, in. I've got to watch the whole thing at once. There we go. And this would be down, up, down, up, down, up, down. 1, 2, 3, 1, 2, 3. Yes. Okay. So these are de Broglie's wavelengths, and these relate to the energy level. So a hydrogen atom that has an electron in the first shell, if we think about Bohr's model, the first shell relates to standing wave with a single wavelength around the atom. The second shell in Bohr's model and the third shell is 2 waves, 3 waves, etc. Okay. Now we know that waves with higher frequency have more energy, so this can make sense as to why lower energy levels have less energy and higher energy levels have more energy. This one would just need to have a higher frequency than this lower one. And it also explains why we can't have all those in between. So we can't have, you know, almost a wave, or we can't have 1 and a bit waves, or down, up, or 2 and a bit waves, right? These can't fit. You'd end up with something like this, which is not matching. There's a mismatch here, right? It's not going to be stable like a standing wave is stable. Okay. So in order to make an electron have a larger amount of energy, you need to take it from having a standing wave of X number of wavelengths, say 1 wavelength to 3 wavelengths. To do that, you need to add in the exact right amount of energy to jump from one to the other. You can't end up in spots in between. They don't work. Okay, this was de Broglie's idea, pretty good idea. Is there any evidence for it? Not really, it just matches really, really well at the time. Uh, However, his idea was endorsed by Einstein, and it wasn't too long before we had some evidence. There were two guys, Davison and Germer, and they accidentally diffracted electrons. So what this means is they had a beam of electrons shooting down. They shot it at a crystal. They weren't supposed to be shooting it at a crystal, but they did. So an object with a crystal structure, right? When those electrons hit the top layer of the crystal structure and the bottom layer of the crystal structure, they ended up interfering with each other, as in the wavelengths of the electrons interfered with each other and created a diffraction pattern. So a pattern of dark and light bands was produced in the detector. Okay, in order to produce dark and light bands, the object needs to diffract, which is, remember, when a wave hits a boundary and spreads out from that boundary, and they also need to interfere, which is when two waves, their peaks and troughs cancel out, or their peaks and peaks add together. These are both properties of waves, and so this experiment showed that electrons have wave behavior, experimentally showed that, which agrees with de Broglie's theory that electrons are waves, which explains Bohr's model. Okay. Oh, and the following formula. So if the so we had the wavelength, we had the momentum of a P equals E over V. We had the momentum of a photon from Einstein's theory of relativity. We've got the energy of a photon as well. So this relates how the frequency of a photon relates to the energy and how the energy and velocity relate to its momentum. Rearranging these two and using momentum, we can get the equation up here, de Broglie's equation. So we've got mv, the momentum, right? That's p. We have h, which is Planck's constant, and we have wavelength, which is just 1 over frequency. All right, and what this equation tells us is if something has a large momentum, you have a very, very tiny number, Planck's constant, divided by a very large number. That means you have a very tiny wavelength. So an object with a large amount of momentum, say for example me, my wavelength is so small that it is impossible to measure. But for objects that are much, much smaller, such as electrons, maybe protons, they have momentums that are small enough so that when you get Planck's constant divided by that momentum, you get a wavelength that is measurable and can have effects such as this diffraction pattern here. All right, next thing, analyze the contribution of Schrödinger to the current model of the atom. Schrödinger. Okay, story time. So once upon a time, there was a guy named Aristotle. He came up with a lot of ideas about how the universe works. People then, for hundreds of years, used his ideas, had their own explanations for how things worked, and they discussed their ideas with each other at length to try and work out what was the truth. Along came a guy named Isaac Newton, and Isaac Newton brought us this idea, F equals ma. Okay? This is an equation that described all forces and motion, right? Described it all. And suddenly, all these scientists who had been discussing ideas, they were now able to verify their ideas mathematically. They were able to describe their ideas mathematically. And if they performed experiments, they could, before they performed the experiments, they could come up with a value of what they should get. Then they'd perform the experiment and see if that's the value they actually got. And if they didn't, they'd realize that something was missing. Now, if something's missing, that means there's new physics to be learnt, and people made a lot of new discoveries based on this. Um, so creating the formula to explain all of motion allowed people to communicate. It allowed people to put their ideas under the same category, and it allowed people to discover new physics. They had a lot more nuance because they had an accurate model, an accurate mathematical model. Then along came that same guy, Einstein, and Einstein said, sorry, Newton, your ideas are good, but I've just got a little bit more to tack on to actually make them correct. And then relativity was born. Unfortunately, relativity is not explaining what's going on in the quantum world. So we have this new branch of physics where um, where waves can be particles, particles can be waves. For some reason, they have quantized amounts of energy based on Planck's constant. Um, and we have lots of scientists with good ideas, and they're discussing their ideas with each other, such as de Broglie discussing his idea of matter waves. But it's hard to be nuanced because um, it's hard to know exactly what outcomes you'd expect from experiments. They had no mathematical model. So in came Schrödinger, just like Isaac Newton came before him, and Schrödinger gave us this equation, Schrödinger's equation. And this equation describes the behavior of one of these matter wave particle things. It describes the behavior of a wavicle. Okay, and suddenly again, just like with Isaac Newton, now scientists can verify their ideas mathematically, they can describe them mathematically, they can predict what should happen in experiments and situations, and when the experiments don't match what they predict, they can realize that there's physics they're missing, they can look into it and discover much more. So, analyze the contribution of Schrödinger to the current model of the atom. He gave us the equation that describes the um, motions of, or describes the waves of the electrons um, more accurately than had ever been done before, which allowed us to then extrapolate and understand a lot more about the universe and everything in quantum physics.